Hello everyone and welcome. Today, we're embarking on an exciting journey into the world of machine learning, specifically deep learning for computer vision. Our mission? To build an intelligent system that can understand and classify hand gestures, a sign language digit recognition model. This project is perfect for B.Tech students like yourselves, as it covers the entire machine learning pipeline. We'll take images of sign digits, process them, build a powerful neural network, train it, and then evaluate just how smart it becomes. Let's start where every data science project begins, loading the data. We're using a fantastic dataset from Kaggle, SignMNIST Train, CSV, and SignMNIST Test, CSV. Pandas is our trusty tool here. We use PD, read CSV, to pull these files directly into our Python environment as data frames. As you can see from train_df, head, each row isn't just numbers. It's a flattened image. The first column is our label, the actual digit 09, represented by the hand sign. The rest are 784 pixel values for a 28x28 grayscale image. And train_df.info gives us a quick summary, confirming we have plenty of data entries and highlighting any potential missing values. In this case, our image data is wonderfully complete. Next up is data preprocessing, preparing our raw images for a neural network. This is where our images truly come to life for the model. NumPy is essential here. Our pixel data is initially flattened into 1D arrays. We use xtrain raw values reshape to transform these into a 3D format. Number_of_ images, 28, 28, 1. That 1 indicates it's a grayscale image. Then, we normalize the pixel values. Images typically have pixel values from 0 to 255. Dividing by 255.0 scales them down to between 0 and 1. This helps our neural network learn faster and more stably. A crucial step for our classification model is one-hot encoding the labels. While the data gives us single digits like 3, our neural network's output layer expects probabilities for each class. So using TensorFlow, Keras, utils, to underscore categorical, a label 3 becomes 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. We dynamically determine num_classes based on the max label in the dataset, ensuring our model correctly handles all unique hand signs. As you can see, we visualize a few sample images from our data. This confirms our reshaping worked perfectly, and we can clearly see the different sign language digits. Finally, we use sklearn, model selection, train_test_split to divide our main training data into a smaller training set for the model to learn from, and a validation set to evaluate its performance during training. This helps us ensure the model generalizes well and doesn't just memorize the training examples. Now for the heart of the project, building the CNN model. We use TensorFlow, Keras to construct our convolutional neural network, which is specifically designed for image data. We start with a sequential model, which is like stacking layers one after another. Our first layer is an input layer, explicitly telling the model to expect images of size 28x28 pixels with one channel. Then come the conv2D layers. These are the workhorses of CNNs. They apply filters to learn spatial features like edges, textures, and patterns in our hand sign images. We stack multiple conv2D layers to learn increasingly complex features. After convolution, we often use max spooling 2D layers. These reduce the size of the feature maps, which helps reduce computation and makes the model more robust to minor shifts in the image. Before feeding into the final classification layers, we flat the 2D feature maps into a single 1D vector. We add a dropout layer to prevent overfitting. It randomly shuts off some neurons during training, forcing the network to learn more robust features. Finally, dense layers. These are standard fully connected neural network layers. Our last dense layer has num_classes outputs, which is 10 for digits 0, 9, or 25 if your dataset includes more ASL signs, and uses a softmax activation to output probabilities for each digit. You can see the model summary, output, showing all our layers, their output shapes, and the total number of trainable parameters in our model. This gives us a good overview of our network's complexity. With our model built, it's time for model training. This is where the CNN learns to recognize the sign language digits. We use model.fit to train our model on x_train_split, our training images, and y_train_split, their one-hot encoded labels. We specify the number of epochs, how many times the model sees the entire dataset, and the batch_size, how many images are processed before the model updates its internal weights. Crucially, we also provide validation_data, x_val_split, and y_val_split. This allows us to monitor the model's performance on data it hasn't seen during training, giving us an honest assessment of its generalization ability. Training is done, but how well did our model actually perform? This is the model evaluation phase. We first use model evaluate on our completely unseen x_test data to get the overall loss and accuracy. Then, we make predictions on x_test and calculate more detailed metrics using Sklern. Metrics. Precision. Out of all the digits our model predicted as x, how many were actually x? Recall. Out of all the images that were truly x, how many did our model correctly identify? F1 score. A balance between precision and recall. The classification report gives us a per-class breakdown of these metrics, letting us see if the model struggles with specific digits. Notice how we dynamically generate target_names to match the actual unique labels present in your dataset, preventing errors from skipped digit labels. This powerful heat map visually summarizes our model's performance. The diagonal elements show correct classifications. For example, predicted 3 when the true label was 3. Off-diagonal elements show misclassifications, where the model got confused. A strong diagonal means a good model. These graphs are vital. The accuracy plot shows training accuracy, blue, and validation accuracy, orange over epochs. Ideally, both should increase and stay close. If the training line goes up but validation plateaus or drops, it indicates overfitting. The loss plot shows the training loss, blue, and validation loss, orange. Both should decrease. Again, a divergence here signals overfitting. Our plots show the model learning well, with training and validation metrics tracking closely. Finally, let's see our model in action with prediction and visualization of sample results. We use Model Predict to generate predictions on a few random images from our test set. For each image, we display the true sign language digit and the model's predicted digit. The text is green if the prediction is correct and red if it's wrong. This gives us intuitive, visual feedback on our model's real-world accuracy. And that wraps up our deep dive into the sign language digit recognition project. You've just seen the entire workflow, from handling raw image data through sophisticated preprocessing, building a powerful convolutional neural network, and thoroughly evaluating its performance. This is a fantastic project to add to your portfolio, showcasing key skills in image classification and deep learning with TensorFlow. Want the code, a step-by-step written guide, or looking for more project ideas? DM us, Sign Language Project, or check out the project resources in our channel description. Don't just learn about AI, build it.
Please do like, share, and subscribe, and DM me if you need any help with your projects.